In this video, we're going to discuss the definite integral. And so this may be new to many of you, but this notation here is what we call a definite integral. And what this is telling us to do is find the area under the curve of f of x from a to b. So we're going to look at an example and see exactly what this tells us, or what we're trying to accomplish here. So if we want to evaluate this definite integral, this is saying to find the area from 0 to 4 under the curve 1/2 x plus 3. So let's start by graphing that. 1/2 x plus 3 we know is a linear function where the y-intercept is 3 and the slope is 1/2. So rise 1, run 2, rise 1, run 2. So we get this linear function. What we're trying to find is the area under that curve from 0 to 4. We're trying to figure out what this area is here. So what I would notice about that shape is that there's two shapes actually in there. What if we split that into a rectangle and a triangle? So we've got two different things that we're going to find the area of. So I'm going to say the area of that underneath that curve would equal the area of that rectangle plus the triangle. So the area of that rectangle, well, area of a rectangle is length times width or width times height, however you want to think about that. But the area of that rectangle would be 4 times 3. The area of a triangle is 1/2 base times height. Well, the width of that base is 4, and the height of that triangle is 2. So I'm going to say the area underneath that curve is 12 plus, this would be 1/2 of 8 is 4. The area underneath is 16. In other words, that red space has an area of 16. So I would say the area, or the definite integral, from 0 to 4 of 1/2 x plus 3 dx equals 16. Now sometimes we don't get nice smooth shapes or easy geometric shapes to find, like we had a rectangle and we had a triangle. When that happens, what we do is we split the entire thing up into rectangles and we add up the area of those rectangles. And just some notation thing to be aware of when we're looking at these problems. N is the number of rectangles and x is the width of each rectangle. A few more definitions. A left-hand sum uses the left-hand endpoints, and a right-hand sum uses right-hand endpoints. So all this may sound a little bit confusing, but once you see an example, hopefully it'll make more sense. So here we've got the same f of x function graphed in two different places. And we're going to use a few different methods to find about what we think the area under this curve is. So this says to find the area, or estimate the area for a left and right hand sum from 0 to 6 of this function, and we're going to use delta x equals 2. In other words, this is the width of the rectangles. So we want each rectangle to be 2y. Alright, so let's look at how we're going to do this. We're going to do what we call a left-hand sum first. So we want each rectangle to be 2y. If we're using a left-hand sum for this width, we're going to use the left-hand endpoint. So I'm going to start, here would be my first rectangle. That is delta x equals 2. Its width is 2. The next rectangle, again, has a width of 2. I would use this left endpoint here. And we're going to add one more rectangle of width 2. And using this left end point, I would use this point here. And so we're going to estimate that from 0 to 6, f of x dx is approximately the sum of all the areas of those rectangles. So what I'm going to do is I'm going to start first by finding the area of the red rectangle. The red rectangle has a height of a little bit more than 20, so I would say that's about 21, and it has a width of 2. Then I'm going to add to that the area of my green rectangle. The green rectangle has a height a little bit above 10. I would guess that looks to me like about 11. So 11 times 2. And then I'm going to add to that the area of my blue rectangle, which would be a height of, it looks like a height of about 5. And again, the width is 2. So the area of the red rectangle would be 42, plus my green rectangle 22, plus the blue rectangle 10. So we're going to estimate the area under the curve from 0 to 6 of f of x dx is approximately 42 plus 22 plus 10. I'm going to estimate that with a left-hand sum that is 64 plus 10. That's about 74. Now notice those rectangles are above the curve. So that is actually an overestimation. So we're going to use the right-hand sum, which should produce then an underestimation. So let's look here. We're going to split this up again into rectangles of widths 2. So we're going to have a rectangle from these 2 points, and we're going to have a rectangle from 2 to 4, and a rectangle from 4 to 6. But now instead we're going to use the right-hand endpoints. So I'm going to split this rectangle up like this using the right endpoint. For the green, using the right endpoint. It would look like this. And then for the blue, I would use this right endpoint. And so I would estimate that area. So let's start with the red first. It has a height, that looks like maybe about 12 times the width of 2. Then we're going to add the green rectangle, which has a height that looks like about 5 and a width of 2. And the blue rectangle, that looks to me like a height of about 3. So the area of the rectangle, the red rectangle, is about 24. The area of the green rectangle is about 10. And the area of the blue rectangle is about 6. Adding all those up, I'm going to estimate that the area under the curve of f of x dx is approximately 34 plus 6, 40. And so what we can reasonably say is the area, the actual area, should be somewhere between 74 and 40. So if we wanted to really do this better, what we should probably do instead is make the rectangles into smaller intervals. So instead of using delta x equals 2, if we use delta x equals 1, we're actually going to do 6 rectangles now. So I'm going to have a rectangle from 0 to 1, from 1 to 2, from 2 to 3, 3 to 4, 4 to 5, and then one from 5 to 6. Okay. So now we're going to go through and we're going to look at finding the area, doing left-hand sums of each one of those. So from 0 to 1, we're going to use this endpoint. from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and then 5 to 6. And so now I would say the area from 0 to 6 of f of x dx is approximately the sum of all those areas. So the first rectangle has a height of about 21 and a width of 1. The next rectangle, the red rectangle, has a height of about 16 times a width of 1. The blue rectangle would be 12 times 1, and so on. The red rectangle, the green rectangle, I'd say that's about 7 times 1. The yellow rectangle, height of 5 times the width of 1. And lastly, the black rectangle has a height of about 3 times 1. So 21 plus 16 plus 12 plus 7 plus 5 plus 3. I would approximate that to an area of about 64. Notice how that is actually between our two previous answers when we did this in the previous slide. Okay, so now we want to talk about how we do this from a table. And what hopefully you notice is we were doing the value of the function times the delta x, the width. So here we're trying to estimate the area under the curve, the definite integral from 0 to 8 of f of x dx. Delta x is the change in x's. So if you notice here, from 0 to 2, 2 to 4, 4 to 6, and 6 to 8. These are all a width of 2. So here I would say delta x equals 2. The left-hand sums correspond from 0 to 2, the value of the function on the left. So if I was going to estimate 0 to 8 of f of x dx, we're going to start first. This is going to actually be the left-hand sums. What we're going to assume is the time from 0 to 2, the height of the function is 11. So we're going to use 2 times 11. Then during the time that the function is going from 2 to 4, we're going to assume the height is 20. So the width is still 2. From 4 to 6, we're going to assume the height of the function is 26. So 26 times 2. And then during the time from 6 to 8, we're going to assume the function's height is 30. So 30 times 2. So I'm going to guess my left-hand sum equals 22 plus 40 plus 52 plus 60. I'm going to guess that the left-hand sum is 174. And so if we're trying to estimate the exact value, we're also going to look at the right hands. So now we're going to look at the rights. So from 0 to 8 of f of x dx. So now what I'm going to guess is over all those interviews, the function is actually at the right-hand point. So during the time from 0 to 2, we're going to assume the height is 20. So 20 times 2. From 2 to 4, we're going to assume the height is 26. From 4 to 6, we're going to assume the height is 30. And from 6 to 8, we're going to assume the height is 42. So I'm going to say that the right equals 40 plus 52 plus 60 plus 84 equals 236. And so what I would say is that we know that the actual area must be in between these two values. So we're going to use an average to estimate. I'm going to say that from 0 to 8 of f of x dx equals the average of these two things. So 174 plus 236 divided by 2 equals 205. In other words, I would guess the area under this f of x function from 0 to 8 is 205.